Welcome to Gradient Daily. Today, we are examining the mechanics of translating standard 2D photographs into fully navigable 360-degree 3D environments. This capability is the focus of research from Jonathan Barron, Ben Mildenhall, Dor Verben, Pratul Sriyabasan, and Peter Hedman at Google Research. Technologies like virtual reality, augmented reality, and autonomous robotics depend on high-fidelity view synthesis to function. However, moving from a static photo to a navigable space is often limited by how accurately a system can reconstruct the world from limited viewpoints. Historically, neural radiance fields operate best on a constrained scale. They are highly effective at reconstructing small, isolated objects that are strictly bounded within a measured volume of space. Look at this split-screen comparison. The left shows a sharp reconstruction of a single object. But when the camera points outward into an environment where the background stretches to the horizon, the rendering breaks down. The foreground holds up, but the distant background degrades into a blurry mess of floating artifacts. This failure occurs because mapping an infinitely deep physical space into a neural network with a rigidly finite capacity creates a scale imbalance. The network lacks the mathematical resolution to process both the inch-wide details of a flower and the mile-wide details of a mountain simultaneously. The researchers developed Mip-NeRF 360 to resolve this imbalance. The architecture uses three distinct innovations: nonlinear spatial parameterization, an online distillation process, and a novel distortion-based regularizer. By addressing this specific scale imbalance, the researchers achieved a 57% reduction in mean squared error compared to previous benchmarks, significantly narrowing the gap between digital reconstruction and the physical scene. To understand why unbounded scenes break down, we have to look at how Mip-NeRF maps space. While a standard NeRF casts infinitely thin 1D rays, a Mip-NeRF casts 3D cones. As seen in this cross-section, the camera casts an expanding cone, forming frustrums. For close objects, these smoothly intersect geometry, solving jagged edges. In an unbounded environment, the cone keeps expanding. Traveling toward the horizon, it becomes infinitely wide. This creates a sampling dilemma. A network evaluates these cones by taking distinct samples along their path. It is mathematically impossible to evenly sample an infinitely expanding volume without exhausting the network's computational budget. If the compute limits how many samples you can take, you end up with massive gaps in distant regions. Forced to process an area it hasn't properly measured, the network averages its best guesses, yielding blurred backgrounds. The base architecture of a NeRF cannot handle infinity by itself. The physical space must be mathematically altered before the network can process it. This brings us to the first architectural shift: nonlinear spatial parameterization. Look at this 3D space grid. An inner boundary, radius 1, is assigned linear high-resolution capacity. Beyond that, a nonlinear contraction applies. Grid lines stretching towards infinity warp and compress, packing tightly inside a finite outer boundary, radius 2. When an expanding cone projects outward and crosses that inner boundary, its infinitely wide distance section is compressed neatly inside the mathematical borders of radius 2. This functions like a fisheye lens. The system maintains metric accuracy in the center while compressing the periphery without discarding the data. Because all spatial coordinates are now strictly bounded between values of 0 and 2, the neural network can ingest and process the background without exceeding its capacity. By mathematically contracting the universe into a finite sphere, Mip-NeRF 360 ensures that close objects remain sharp, while guaranteeing that distant landscapes are actually renderable. Bounding the space introduces a secondary bottleneck. Even inside a contracted sphere, uniformly taking samples along a cone means most of the computational power is wasted checking empty air. To solve this, the architecture deploys online distillation through a dual network setup. A lightweight network, the proposal MLP, rapidly scans along a ray. It maps out a rough curve graph where elevated peaks indicate the likely locations of physical surfaces. Once mapped, the much larger NeRF MLP takes over. It receives only those specific peak coordinates, bypassing the empty regions where no geometry exists. The relationship is highly specialized. One acts as a scout, rapidly scanning the area with low resolution, so the other can operate like a sniper, executing high-precision rendering exactly where the surfaces are. The distillation is online because these two networks train simultaneously. As they iterate, the proposal MLP dynamically learns to chitin its predictions, continuously narrowing the search area for the larger network. Even though the architecture adds a second network, overall training remains tractable because of the massive reduction in wasted processing cycles. Distillation decouples the search for geometry from the rendering of final detail, bringing efficiency to the processing of 360-degree environments. There is one final rendering artifact: floaters. When a network attempts to simulate a background, it often cheats by generating semi-transparent clouds of density directly in front of the camera. To eliminate this, the team implemented a distortion-based regularizer. We can see the mechanics of this penalty here. When calculating opacity, the network might spread values across multiple scattered peaks, creating dispersed fog. The new regularizer penalizes this split, forcing those scattered peaks to collapse into one sharp spike. This forces the network to commit to a single solid depth plane instead of rendering scattered layers of mist. This regularizer anchors the structural integrity of the scene. It prevents the network from hallucinating floaters and ensures the underlying 3D geometry is accurate. To validate these systems, Google Research built a custom 360 dataset, using a camera rig to capture intricate environments from complete spherical angles. The performance data on this chart shows the result. Against the original Mip-NeRF baseline, Mip-NeRF 360 reduces the mean squared error by 57%. The success of the model is evident in the generated depth maps. These maps show the network accurately reconstructing the geometry of objects miles from the camera. Practical limitations remain. Training dual networks on high-resolution, unbounded images is a compute-intensive process that demands significant hardware. Future work will likely focus on migrating this unbounded architecture into real-time rendering frameworks to increase deployment speed. Infinite space, mathematically contracted. Dual network distillation, optimizing compute. And a penalty, enforcing solid geometry. Mip-NeRF 360 demonstrates that neural networks are no longer constrained to small objects on a pedestal. They can now reconstruct the entirety of an unbounded world. Thank you for watching Gradient Daily. If you found this breakdown valuable, please like the video and subscribe to the channel to keep up with our coverage of the latest research in neural networks.